Okay, so page 281 of the packet, number 6. So determine the resistance of the shunt picture in 12.6. Made of constantin, which is resistivity of 0.49 times 10 to the negative 6. That's a huge resistivity. That's ohm meters. At 20 degrees Celsius. Use the central cross section to compute the area. So what we've got here is we've got air gaps here. So what we have here is several layers that are 12 millimeters wide and 2 millimeters thick. And it appears to be 5 of those. The air gap in between does not matter. The air gap is for cooling because that high of resistance is going to produce a lot of heat. So the cross-sectional area here is just going to be 12 millimeters by 2 millimeters times 5. So that's going to be 120 millimeters squared. The length, no, that 12. Yeah, it would be 12 centimeters. You are correct. Length is 12 centimeters. So then, we're looking for the resistance. We're going to assume that it's operating at 20 degrees, so it doesn't give us any other operational temperature. So the resistance there is found by, remember the formula? Resistivity times length divided by cross-sectional area, right? And remember, even though the resistivity is times 10 to the negative 6, that's in ohm meters, because this is in square millimeters. Let me get back here. Yeah. Oh, come on now. 1 meter squared is 10 to the 6th millimeters squared. So because of that conversion, that cancels out that 10 to the negative 6. So what we're looking at here is we've got the 0.49. And again, we're ignoring that 10 to the negative 6 because it's canceled out in our units. Times the length. Now this has to be in meters. That's going to be 0.12 is that length over the 120. So what's that come out to be? 0.49 times 0.12 divided by 120. Get a resistance of 4.9 times 10 to the negative 4th, so 0.00049 ohms is what we're getting for resistance out of that. Okay. Let's take a peek. So page 283, number 4. We have determined the resistance of a copper wire within an inductor was measured and found to be, so 2.78 ohms at 28 degrees. After several hours of operation, the resistance was at 3.34. Okay, so we got 2.78, 3.34. Remember the magic number is 234.5, right? For temperature, yes. So the 2.78 is at 234.5 plus 28. And then this is going to be 234.5 plus whatever that missing temperature is. So we're going to add those together, which is going to give us 262.5. And we'll cross multiply 3.34 times 262.5 divided by 2.78. Gives us 315 point, where are you? 38, we'll call it, is equal to this. 234.5 plus t. Then we just solve for t. Subtract the 234.5. What do we get? 80.88, I think. So that comes out to be. So that's heating up to 80.88 degrees. That's a significant heat. Any other questions? Okay, well, so we have the next 2 days to learn about number system. To do that, we need to take a closer look at our own numbering system. What we have is called a decimal number system. Decimal means base 10. What that means is the place values in our number system are based off of powers of 10. This is the ones digit, the tens digit, hundreds digit, thousands, 10,000s, and so on. Well, with what we know of our powers, 1 is really just 10 to the power of 0. 10 is 10 to the power of 1. 100 is 10 to the power of 2. 1,000 is 10 to the third. 10 to the fourth is 10,000. 10 to the fifth, and so on. Those place values are just determined by powers of 10, even into the decimals. 1/10 is just 10 to the power of -1. 10 to the -2 is 1/100th, and continuing on in that direction. If I put in a number like 328, that is just saying that this is 3 times 100 plus 2 times 10 plus 8 times 1. Now it's just convenient that in this number system, in this base, it's still just 328 when they add it up. That's how the number system is designed. That's why we use 10 as our base. We can use other bases, though, for numbering systems. For example, there's octal numbers. Octal numbers are base 8. So what that means is the place values here are not powers of 10 anymore. They're powers of 8. So this is 8 to the 0. In fact, I'm going to leave a little space here. 8 to the 0, and 8 to the power of 1, and 8 squared, and 8 to the third, and 8 to the fourth, and 8 to the fifth, and so on. Well, what is 8 to the power of 0? 1. 8 to the power of 1? 8. 8 squared? 64. 8 to the power of 3? 512. 8 to the power of 4? 4,096. 8 to the power of 5? What's 700? That's not right. 32,768, is that right? 32,768. That's probably as far as we need to go. Going in the other direction, 8 to the -1, 8 to the -2, 8 to the -3, and so on. Well, 8 to the -1 is just 1/8. 8 to the -2 is 1 over 64. 8 to the -3 is 1 over 512. And we can keep going. So if I give you the octal number, now first of all, I should point out here, in base 10, what's the largest digit I can have in any place value? It's a 9. Very good. One less than 10. In base 8, what do you think the largest digit is going to be? 7. Good. Because at 8, it would carry over into the next place value. So let's have the number 5364 here. That's the octal number 5364. Now the notation we would use, it would look like this. That little 8 down there is indicating that's base 8. There are other notations, but that's the most common one. To translate that into base 10, we would have to take each digit times its place value. So the 5 is in what place value? 512. What's that at? What's that multiply out to? 2560. The 3 is in what place value? 64. 3 times 64? 192. The 6 is in the 8th place. 6 times 8? 48. And finally, the 4 is in the 1's place. It's just a 4. So if we add that all up, what do we get? 2804? Oops. Is that what that adds up to? So the octal number 5364 is equivalent to our decimal number, base 10 number, 2,804. Does that make sense? So what if I want to convert 3,209 base 8 into decimal base 10? The 3 is in what place value? If we look up here, that place value would be the 512, right? 8 to the third. So 3 times 512 is 1536. The 2 is in which place value? 64. 2 times 64 is 128. The 0 doesn't matter. It has 0 value no matter what the place value is. 9 is in the 1's place. So the octal number, base 8, 3209, notice I don't say 3,209 because those are not place values. It's 3209 octal, is equivalent to the base 10 number, 1,673. I'm going to have you guys try one. We're going to take the octal number, 7231, convert it into base 10. I'll give you a couple minutes to do that. Okay, so the 7 is the 512's place value. 7 times 512 is perfect. The 2 is in the 64's place value. 2 times 64, 128. 3 is in the 8's place value. 3 times 8, 24. And the 1 is in the 1's place value. 1 times 1 is 1. Good. So we've got what? 17, 13, 7, and 3. So the octal number 7231 comes out to base 10, 3737. Is that what you got? Any questions? Well, how about going the other way? What if I give you a base 10 number? What if I give you base 10? Let's do 2939. And I want you to convert it into base 8, octal. Well, first thing we have to do is we have to look at our number line. And we have to find what is the largest place value that is smaller than 2939. Well, 32,000 is definitely too big. So the next one we have is the 512, right? So 2,939, how many times does 512 go into that? 5 times, very good. So here's what I'm gonna do, is I'm gonna put a 5 here in that 512's digit. 5 times 512 is 2560, correct? I subtract that, what's left? 379. What's my next digit? 64. How many times does 64 go into 379? 5 times. 5 times 64 would be 320. So I'm going to put a 5 in the 64 place value. Subtracting 320 leaves me with 59. My next place value is 8. How many times does 8 go into 59? 7, right? Put a 7 there in the 8's place. 7 times 8 is 56, which means there's how much left? 3. So that 3 would go in the 1's place. So the base 10 number, 2,939, in base 8 is 5573. Let's try base 10, 999, going into octal. Make it a little simpler, I'm just going to write in our place values there. 512, how many times does it go into this? Once. Very good. I'm going to put a 1 on the 512. 1 times 512 is just 512. I subtract, get 487. Moving on, the 64 is the next place value. How many times does 64 go into 487? Try 7. That's going to be, what, 448? I'll put 7 in the 64. I subtract there, and I'm going to get that 39. Next, I have the 8's place value. How many times does 8 go into 39? 4 will work. 4 times 8 is 32. Subtract, we get 7. Those 7 ones go in the 1's. So the base 10 number, 999, becomes 1747 octal. What do you think? Having fun yet? In your notes, convert. Base 10. $32,799 into base 8. I'll give you some time. Let's make this 32,799. Let's make it 32,719. How's that? If we look at this, we have to ask what is the largest place value that is still smaller than the 32,000? Well, the 32,768 is too big. We can't use that one. So we go down to the 4,096. 4,096 goes in there 7 times. 4096 times 7 is 28,672. So that goes in there 7 times. We subtract here. 4,047 is what's left, right? Next, we move on to the 512. 512 goes into 4,000 how many times? Let's try 7. Oops. So 7 times 512 is 3,584. We subtract that. 463 left over. Now we look at that 463. 64 goes into that how many times? 7. So I'll put 7 here in the 64 digit. 7 times 64 is 448. We subtract that is 15. Now we are left with the 8's digit. 8 goes in there how many times? Once. So we put a 1 in the 8's digit. We subtract the 8 to get 7 left. So that goes there. So 32,719 base 10 becomes 77717 octal. What do you think? Good stuff? Any questions? Let me know because there is a test. Okay, well, the next step, as we move on from octal numbers, let's talk about hexadecimal numbers. Hexadecimal is base 16. Now the problem here is base 16 means the largest digit is going to be what? 15. Well, that's going to be kind of awkward once you get past 9. So what they do is once they get past 9, 9 is just a 9. 10 is represented by the letter A. 11 is represented by B. 12 is C. 13 is D. 14 is the letter E. And 15 is the letter F. Our place values Well, this is 16 to the power of 0, which is 1. 16 to the power of 1, which is 16. 16 to the power of 2 is 256. 16 to the power of 3 is 4,096. 16 to the power of 4 is 65,000. I'm blacking out on what's the rest. Oh, type 536. You see, they get very big very, very fast. Going this way, this is 16 to the negative 1, that's 1/16. 16 to the negative 2, that's 1 out of 256. Probably don't need to go any further than that. So if I have a hexadecimal number, 2B5F, so 2B5F hex going to base 10. We again just have to go by the place values. The 2 is in what place value? 4,096. Says 8,192. B, which stands for what? 11, is in the 256 place value. So that is going to be 2,816. Is that right? 5 is in the 16's place, which is 80. And F, which stands for 15, is in the 1's place. So we add those all up. We get 11,103 base 10. So 2B5F hex is equivalent, hexadecimal is equivalent to 11,103 base 10. What do you think? Cool stuff? In your notes, I want you to try this one. FACE base 10, or base 16, sorry, hex, is what base 10? Convert that. Okay, so F is in which place value? Remember, that would be the 4,096 place, right? So 15 is what F stands for, times 4096 is going to get large in a hurry. 61,440. A, which is 10, is in the 256 place. So that's 2,560. C, which stands for 12, is in the 16 place. 12 times 16 is 192. And E, which is 14, is in the 1's place. So that's just 14. So that adds up to be 6. 1, what do we got there? 2. Is that 64,216? Does that work? Did I add those right? 206. Oh, yep, I carried a 1 when I shouldn't have. 64,206. So FACE hexadecimal is equivalent to 64,216 or 206 in base 10. Going the other way works exactly the same. Let's say I have, let's just do the number 6,000 base 10. And I want to convert it into hexadecimal. Well, the largest place value that's going to go into that is the 4,096. So let's go through that. 4,096 is going to go in there once. So that's going to give me 1,904 left over. So I got 1 in the 4,096 place. Let's get in there. Next is the 256 place. 256 goes into 904 how many times? Try 3. That's 768. We subtract. Is that 136 that's left? So it goes in there 3 times. 16 into 136. I'm going to say 8. Was that 128 then? Leaving us with 8 left. So 16 went in there 8 times. Come on now. And there's 8 ones left over. So 6,000 base 10 is 1388 in hexadecimal. Didn't get any letters in that conversion. The big kahuna is binary, which is base 2. Being base 2, the largest digit is what? 1. So every digit's either a 0 or a 1. Now, we don't have the commas really that we put in there. I'm just putting in there for me to keep track. This first digit is 2 to the 0 or 1. Next one's 2 to the 1 or 2. 2 to the second or 4. 2 to the third or 8. 2 to the fourth, 16. 2 to the fifth, 32nd. 2 to the sixth, 64. 128. 256. And 512. Going the other way, to the negative 1, this would be the 1/2 digit. To the negative 2, this would be the 1/4 digit, and so on. So the binary number 101101. That little 2 again indicates it's binary. Converting that into base 10. The first 1 is how much? Is what place value? 64. So 1 times 64 is 64. That 0 doesn't matter. This 1 is in the 16 digit. 1 times 16 is 16. The next one is in the 8 digit. That's 8. The next one is in the 4 digit. 1 times 4 is 4. 0 doesn't matter, and the final 1 is in the 1's digit. So we add those all up. We got what? 10, 22, 23, carry the 2, 8, 9, 93. So the binary number 101101 is equivalent to 93 base 10. Now we're going to do this conversion back and forth between binary and base quite a bit over the next couple of days. But before you leave here today, I want to ask the question, why octal and hexadecimal? I'm sure you understand the binary, reason for binary, because in a computer, the way a computer thinks is either on or off. A 1 is on, a 0 is off. Everything in a computer is stored binary. A bit in a computer is considered to be one binary digit. It's a switch that's either turned on or off. So binary makes sense. Well, the reason we do octal and hexadecimal is very simple. Let's express the number 99 in both, that's base 10, of course. Let's express it in both binary, and then we're going to express it again in hexadecimal. In binary, the largest digit that goes into 99 is a 64. That goes in there once. We subtract 64, leaves us with 35. A 32 goes in there once. We subtract 32, leaves us with 3. 16 doesn't go in there. 8 doesn't go in there. 4 doesn't go in there. 2 goes in there once. Leaves us with 1, so there's a 1. So in hexadecimal, or sorry, in binary, 99 is 11000011. In hexadecimal, well, our place values, we're going to need the 16 and the 1s. 16 goes into 99 5 times. Nope, 6 times, sorry. 6 times. 6 times 16 is 96. There's 3 left over. So in hexadecimal, 63 represents 99. If I look at my binary number here, 2 to the power of 4 equals 16, correct? What that means is I can take 4 binary digits and use them to create one hexadecimal digit. So 1, 2, 3, 4, I cut that off there. There's only 3 more. In binary, 0, 0, 1, 1, that's 1, 2, 4, 8. That stands for 3, doesn't it? Does that make sense? This part here, 1, 1, 0, again, that's 1, 2, 4. That would stand for 6. Huh, what a coincidence. I can take a binary number and starting at the end, go in groups of 4 bits, and each of those 4-bit groups creates a digit in a hexadecimal number. We are out of time, so we're going to look at this more tomorrow. I'm going to give you a packet and pick through the packet. In this packet, there's converting, and then there's also operations with the different numbers. Just do the converting in the packet for now.